Hello everyone. In this short video, let's have a chat about congestion control. So, which is the core part of TCP protocol, and because TCP it dominates the internet traffic, so understanding how TCP congestion control work is important, and also it's critical if in the future you want to design your own version or a smarter version of congestion control algorithm. Okay, so a big question here is when we are doing congestion control, so what are we really controlling? Now, think of congestion control is any controlling system. So there must be some parameters that we can play with. We can adjust its value. So this parameter in congestion control is called a congestion window. So I drop it here. And we call it short for CWND. So it's a value parameter, and usually if we say a congestion window equals 10, what does that mean? So that means we can TCP sender can send out 10 segments together without waiting for an acknowledgement for each segment. Okay. So this is a big improvement comparing to traditional stop and wait protocol where we can only send one segment. Now, the problem is how big is this congestion window we can have, or what is the optimal value for this congestion window. So this is actually what different congestion control protocol focus on to decide the size of the congestion window, or in other words, to decide how many segments we can send out without waiting for acknowledgement for each. So sometimes we also call it the in-flight traffic. Okay. So traditionally, most TCP congestion control using an algorithm which you may have heard of called AIMD. Okay, AIMD. So which means if the network is good, so we adaptively increase the congestion window size. When the network is getting poor, or we notice there's a congestion happen, we decrease the congestion window hardly or multiplicatively. So this is the key idea behind the AIMD. Okay, so what as a result you may notice, let's say a congestion window, initially it will increase fast. This is also called a slow start phase. And then gradually, if there's no congestion, it will linearly more carefully increase the congestion window. Unless there is a congestion happen, let's say a packet loss, the congestion window will be immediately reset either to 1 or to half of the window, depending on different type of the congestion control. So this pattern will continue, right? And we can see this is a typical sawtooth pattern for congestion window. And this type of congestion control is also called loss-based because we consider loss is a message for congestion. But the problem is when we sing a loss, that means either the bottleneck link buffer or the receiver's buffer has already been overflow, which is not good. So somehow we should try to avoid that happen. Now, Google developed a different way of congestion control to adjust the congestion window size, which utilize an equation between bottleneck bandwidth times the delay. So the delay here is the round trip time, also called BDP. P is a product of the two value. So Google's algorithm using this BDP value as the congestion window size, and Google gave this algorithm a name called BBR, bottleneck bandwidth and round trip time congestion control. And the experiments have shown that BBR can significantly improve throughput and reduce latency, improving video streaming. And in fact, Google has using this congestion control in many of the Google products like Google Cloud, YouTube, and also BBR has been is a part of the modern Linux kernel. So if you look at AIMD is kind of the signal or loss event-based congestion control. The BBR use a model or equation, so it's a model-based congestion control. So totally different way doing that. And how to find an optimal congestion window is still a very active area in the computer networking field. And many machine learning and even reinforcement learning, deep learning has been developed to help find a better value of congestion window rather than the way like in AMD and BBR. Okay. Now, because congestion window stays in the TCP sender, is it the only window at TCP sender? No, there is another window. So let's have a quick look. So the other window inside TCP sender is called a receive window. That's short for RWND. Okay. So in fact, both windows will consist the core part of a TCP sender. Okay. So what is receiver window mean? So this is another parameter that is indicate how much capacity the receiver's buffer is. Okay, so this value is initialized by the receiver during the three-way handshake stage, and this window, the receive window, is actually stays with every single TCP packet because it is inside a TCP header, which is typically 16 bytes, while congestion window is not part of TCP header. It was stored in sender's memory. So this is a key difference. Okay. So usually when we talk about flow control, we are actually controlling the receiver's window. And when we talk about congestion control, we are actually controlling the congestion window. Okay. Now, what is the ultimate goal for a TCP sender? Now, it is decide the sending rate. Okay, sending rate simply for the application, how much data rate we can send out from a sender, no matter it's decided by the receiver window or congestion window. So the sending rate, it's now let's look at the sending rate. So this equals the actually the minimal value between the receive window and the congestion window. So why? So design logic behind is when we decide ascending rate, so we should not overload the network and we should not overload the receiver. Okay, so to not overload the network, we should ensure that the sending rate is not more higher than the congestion window, because that reflects the bottleneck link. And to not overwhelm the receiver, like a consumer device, and obviously it depends on the receiver's buffer, which is decided by the receiver window. So that means, as a result, sending rate is a minimal value between the two. Okay. So I hope this video can help you understand what is Windows and what is congestion control really controlling, right? Okay, thank you.